Stephen Hawking, the renowned theoretical physicist, proposed a scientific explanation for the beginning of the universe based on his work in the fields of cosmology and quantum mechanics. His ideas are mainly summarized in the theory known as Hawking's model of the universe. According to Hawking's model, the universe began with the Big Bang. This concept is widely accepted in modern cosmology and suggests that the universe originated from an extremely hot and dense state approximately 13.8 billion years ago. At this moment of the Big Bang, all matter, energy, space, and time came into existence. One of the key elements of Hawking's model is the application of quantum mechanics to the early universe. He proposed that during the first moments after the Big Bang, the universe was governed by the laws of quantum physics, which means that the usual concepts of space and time, as we know them, lose their conventional meaning at such extreme scales. Hawking introduced the concept of imaginary time to describe the state of the universe at the very beginning. In the context of his theory, imaginary time behaves like a fourth dimension alongside the three spatial dimensions we experience in our everyday lives. Imaginary time is not imaginary in the sense of being fictional. Rather, it is a mathematical concept that allows physicists to work with certain equations more easily. Hawking's work also explored the role of black holes in the early universe. He proposed that at the time of the Big Bang, there were tiny primordial black holes. These microscopic black holes were a product of the extreme conditions during the early moments of the universe. Over time, these black holes would have evaporated through a process known as Hawking radiation, which is a quantum effect predicted by Stephen Hawking. This radiation is essentially a stream of particles emitted by the black hole, causing it to lose mass and eventually disappear entirely. Other prominent theories, such as inflationary cosmology and string theory, also contribute to our understanding of the universe's origin and development. Inflationary cosmology is a theoretical framework in modern cosmology that addresses several long-standing puzzles and provides an elegant explanation for the large-scale structure and uniformity of the universe that we observe today. The theory proposes that the early universe underwent a rapid and exponential expansion phase called cosmic inflation shortly after the Big Bang. The concept of inflation was first introduced in the early 1980s by physicists Alan Guth, Andre Linde, and others to solve certain problems in standard Big Bang cosmology. Some of the key aspects and implications of inflationary cosmology include homogeneity and isotropy. The universe appears remarkably uniform and isotropic, the same in all directions, on large scales. Inflation explains this by proposing that during the exponential expansion phase, different regions of the universe were stretched to become nearly identical, explaining the observed uniformity we see in the cosmic microwave background radiation and large-scale structure. Horizon problem. According to the Big Bang theory, regions of the universe that are now widely separated were once in causal contact, meaning they could interact and exchange information through the exchange of light signals. However, the observed uniformity of the universe suggests that these regions have never been in contact since the beginning of the universe. Inflation resolves this problem by proposing that all observable regions were once close together before the rapid expansion, allowing them to reach a uniform temperature and density. Flatness problem. The universe appears to be very flat, meaning its geometry is very close to being Euclidean. However, standard cosmology suggests that the universe should curve over time, open or closed geometry. Inflation naturally drives the geometry of the universe towards being flat, explaining why the curvature is nearly zero. Seed density perturbations. Inflation provides a mechanism for generating tiny quantum fluctuations in the early universe, which later grew into the large-scale structures like galaxies and galaxy clusters that we see today. These initial fluctuations in density served as seeds for the formation of cosmic structures as the universe expanded and evolved. Inflationary cosmology has gained substantial support over the years due to its ability to explain various observed features of the universe. It is consistent with the cosmic microwave background radiation measurements made by satellites like the Cosmic Microwave Background Explorer, (COBE), and the Planck spacecraft. Moreover, inflationary models have been successful in predicting the large-scale distribution of galaxies and the anisotropies in the cosmic microwave background. While inflation has been highly successful in addressing many cosmological puzzles, there are still open questions and challenges in understanding the details of the inflationary process and its connection to other fundamental theories, such as quantum gravity. String theory is a theoretical framework in theoretical physics that attempts to describe the fundamental structure of the universe at the most fundamental level. It is often regarded as a candidate for a theory of everything, a unified theory that combines all the known fundamental forces and particles in physics. At its core, string theory proposes that elementary particles, such as electrons and quarks, are not point-like particles as assumed in traditional particle physics, but instead, they are tiny, one-dimensional objects called strings. These strings are extremely small, with a size on the order of the Planck length, which is about 10⁻35 meters. The fundamental building blocks of the universe in string theory are these vibrating strings. The different vibrational modes of strings give rise to the various particles and force carriers found in the standard model of particle physics, including photons, gluons, and the particles of the Higgs field. Key features and concepts of string theory include unification of forces. String theory attempts to unify all the fundamental forces of nature, gravity, electromagnetism, the weak nuclear force, and the strong nuclear force, into a single, coherent framework. In the standard model, gravity is described by Einstein's general relativity, while the other forces are described by quantum field theories. Extra dimensions. String theory requires extra spatial dimensions beyond the usual 3 dimensions of length, width, and height. These extra dimensions may be compactified or curled up at incredibly tiny scales, making them effectively unobservable at current energies. Dualities. String theory exhibits a remarkable property known as duality. Dualities suggest that different string theories or different compactifications of the extra dimensions can be physically equivalent, describing the same physical phenomena in different ways. This has led to the understanding that different string theories might be different aspects of a single underlying theory, referred to as M-theory. Challenges. Despite its elegance and potential, string theory faces several significant challenges. For one, it has not yet made specific testable predictions that could be experimentally confirmed, partly due to the extremely high energies required to probe the Planck scale. Additionally, there are many possible ways to compactify the extra dimensions, resulting in an enormous number of potential string theory solutions, making it challenging to pinpoint the unique description of our universe. While string theory remains an active area of research, it has already had a profound impact on theoretical physics. It has inspired new ideas in mathematics, such as developments in algebraic geometry, and has led to a deeper understanding of black hole physics and other areas of quantum gravity. The Big Bang is the prevailing scientific theory that describes the origin and early development of the universe. It is supported by a vast amount of observational evidence and is widely accepted among cosmologists and astrophysicists. Here's a more detailed explanation of what we know about the Big Bang. Origin of the universe. The Big Bang theory posits that the universe began as a singularity, an infinitely small, hot, and dense point, roughly 13.8 billion years ago. At this initial moment, all the matter, energy, space, and time we know today came into existence. Expansion of the universe. After the Big Bang, the universe rapidly expanded and continues to expand to this day. This expansion is not like an explosion in space. Rather, it is the expansion of space itself. The best analogy is to think of the universe as a balloon being inflated, with galaxies and other cosmic structures moving away from each other as the balloon expands. Cosmic microwave background, CMB. One of the most significant pieces of evidence supporting the Big Bang theory is the discovery of the cosmic microwave background radiation. About 380,000 years after the Big Bang, the universe had cooled enough for protons and electrons to combine and form neutral atoms, allowing photons, particles of light, to travel freely through space. The CMB is the remnant glow of these photons, and it permeates the entire universe. It was first detected in 1965 and provides strong evidence that the universe was once in an extremely hot and dense state. Formation of elements. During the first few minutes after the Big Bang, when the universe was still incredibly hot and dense, nuclear reactions occurred, creating the primordial elements, hydrogen, helium, and trace amounts of lithium and beryllium. These elements are the building blocks of stars, galaxies, and ultimately, all the matter we see around us today. Large-scale structure. As the universe expanded and cooled further, slight fluctuations in the density of matter emerged. These fluctuations served as seeds for the formation of structures in the universe, such as galaxies and galaxy clusters. The gravitational pull of these regions of higher density led to the formation of cosmic structures over billions of years. Dark matter and dark energy. The Big Bang theory also accounts for the existence of dark matter and dark energy, which are two mysterious components of the universe. Dark matter is an invisible and elusive form of matter that exerts gravitational influence on visible matter, helping to shape the large-scale structure of the universe. Dark energy, on the other hand, is a mysterious force that appears to be responsible for the accelerated expansion of the universe. While the Big Bang theory provides a robust framework for understanding the early universe and its evolution, there are still open questions and ongoing research to better understand certain aspects, such as the nature of dark matter and dark energy, the early moments of the universe, and how to reconcile the theory with quantum mechanics in the context of a unified theory of everything. Nonetheless, it remains one of the most successful and fundamental theories in modern cosmology.